Okay, I need you to settle down because we are a little bit behind and I want us to get started. There are people online that are waiting. So just a friendly reminder, we like to start every day with this friendly reminder about our code of conduct. I shared this yesterday and I'll share it every day. Very simple, being human, being patient with one another, being respectful of one another. I also want to remind us of why we're all here. And remind us of our ground rules. Just remind our speakers and any of our presenters to please disclose your relationships with companies and not-for-profit organizations in the CDR realm when you get up to speak. That is all I have to say. So I'm going to get us started with the breakout reports, starting with session 1 yesterday. Breakout.
Okay, thanks. I think, so I'm representing group 1 and yeah, we decided to break this down into pieces. And so what I'm going to do, session 1. And so we're going to break this down into pieces. And so just a reminder, the questions were MRV efforts from non-ocean-based CDR, things to emulate, things to avoid. What more do you wish you knew to inform your answer? And so what I'm going to do is just highlight some of the key takeaways and learnings from across the groups from non-ocean-based CDR. So the first point was that oceans raise different MRV requirements than terrestrial systems, but there are opportunities to learn, including difficulties, mistakes, and dangers. There's still a lot of concern about the variability and accuracy of models and methods used in forestry and agriculture. So clearly there's learnings, but we'll have to do some of our own learnings as well. There's a strong desire for an MRV framework in order to address concerns about standards, baseline site locations, acceptability, uncertainty thresholds, and so on. There is investment in the community resources for MRV, but that we also recognize that there'll be some level of international coordination needed, similar to some of the organic markets that have formed, but perhaps also some government organization. One of the differences we highlighted is potentially closed versus open systems, comparing terrestrial versus open ocean or ocean. And there's big challenges for scale for doing marine CDR and MRV event marine CDR. The ocean doesn't quite have the same opportunity as the carbon plus model on top of forestry and agricultural industries. And what we mean by that is that in a lot of those systems, there's additional benefits from generating carbon. And so example, forest management practices to reduce wildfire risks, regenerative farming practices, and so on. And so the ocean doesn't always have those opportunities like terrestrial systems do. One of the big differences between ocean and terrestrial was ownership. Most land is owned, most ocean is not. It's a commons, so there can be tragedy there, but also permitting issues, tragedy of the commons, but also permitting issues. Finally, or second to last, registry and verification are still up in the air, and certainly for marine systems, but we can learn stuff from the terrestrial folks. And finally, well-executed forestry projects do seem to have a very positive impact on local communities and other benefits, and so we feel like we can learn from that from marine systems. Thank you.
Thanks, Zach. I'm Claire Reimers, and I led one of the other breakout groups. And so I'm going to just address some of the concerns that were raised by the different breakout groups yesterday after session 1. The greatest concern for MRV and marine CDR moving forward is transparency. And I think that speaks for itself. There's also concern about the overall balancing the urgency to start these experiments, the urgency of climate change, but also balancing that with the doing things carefully and having quality measurements that we can believe. We want to prioritize flexibility moving forward and creativity. So not get so hyper-focused on MRV that we prevent things from moving forward. Another concern, of course, raised, which I think will come up again and again, is permitting. It just doesn't exist yet. Other things raised were, we have these different cultures here, so how do we manage the kind of pace that academic science and government works at compared to industry? What are some of the incentive challenges? And then the scale of the ocean creates new demands for data, but opens questions for the use of models and the direct measurement, and where direct measurements aren't possible. And then just a reminder that all this exists in the context of the carbon market, and companies may be more incentivized to invest in decarbonization versus purchasing carbon credits. So I will turn over, I think Chris will be next.
Thanks, I'm Chris Hunt. I'm really quickly just going to go over a few key questions that were brought up among the session leaders. I think one of the big ones that I'm sure was really common was the sort of interest or the desire for some sort of governance structure. But then that brought about the question of who provides that governance and what does it look like? The problems and the potential solutions that we're talking about here are transnational. They cross boundaries, political spectrums, and pretty much everything. And so forming a governance structure would be a big challenge, but would also help provide a lot of guidance instead of a more decentralized approach. To that end, how could a governance structure or a market for marine CDR be more unified than the impression that at least that we got from the descriptions of the terrestrial markets? It sounded like the terrestrial markets were fairly open, but also fairly chaotic. And there was perhaps a lack of trust and transparency in some of those markets. Would governance restrict a market-based approach, or could they work together? You know, are the two going to be in opposition to each other? There was a desire or an interest in standards. The standards would have to come out of aggregation, but there's a question of what exactly are you aggregating when you form those standards? And then on the flip side, how do we emulate the terrestrial companies or markets that are doing good self-MRV? What are their best practices? How can we make the good companies win or incentive, or like, yeah, how do the good companies succeed and avoid this sort of race to the cheapest credit or race to the bottom that was mentioned yesterday as well? One big question is, who pays for MRV? Is it the companies that are producing the credits, or is it some other body that has that responsibility? Where should mCDR happen? I think that means sort of spatially. Do we have the models and the background data to know that and to make those decisions yet? And finally, who would assume the risk of negative impacts? So if a project goes sideways or produces unintended consequences that we don't anticipate, then who does the responsibility fall to for that negative impact, and who assumes that risk perhaps at the top? And so with that, I'll hand it off to Wiley, who will talk about actions.
Hi, I'm Wiley Wolf, and we're just going to do a couple of quick actions to wrap this up. Our first action is measure and understand baselines now before marine CDR gets underway and starts to perturbate a system. We want to move fast with hypothesis-driven experiments without losing the trust in carbon markets, legislators, or local communities. Alongside that hypothesis-driven experiments, we need to iteratively develop MRV techniques, which will evolve as our understanding of the science evolves. We need sustained funding for improved sensors, both manned and autonomous, as well as model validation beyond sporadic funding like XPRIZE. And then we need to put a price on CO2 permanence. A project that is 10 years and a project that's 1,000 years have inherently different value, and that's not reflected in carbon markets. That's it.
Sir, please say your name and.
Are there notes available?
What's that?
Are there notes available? For
Yeah, they're on that computer.
Great.
No worries, just a sec.
I've kind of memorized my bit. While she's doing that, I'm Jacob Cram. I'm from the University of Maryland, Center for Environmental Science. I have no affiliations with companies or nonprofits. And in terms of the structure of our science, I mean, like group one, we are summarizing a summary for you. And so we have a couple different sections. I'm going to cover the first one, and then I'll pass it off to Mallory. There are, as you can see, there's 3 bullets under the section of takeaways and learning existing CDR. First, I want to mention that there's Dave's talk yesterday sparked a really interesting discussion, at least for some of the groups, about sort of the order of operations, right? Between the horse. And there's, at least in our group, there was some pushback against that, saying that there isn't very much time, and getting mCDR right concurrently with the research is an important priority. Other things that came up, there's sort of comparisons to the terrestrial space, that there, that there are different kinds of systems, different challenges. One thing, yes. Be close to the mic, please, and say I did say my name. My name is Jacob Cram, and I wasn't speaking into the mic. It's true. What? Fine. Feel very uncomfortable. One of the big differences is that ocean water moves around. So then you have this challenge of, do you think of it through how do you integrate the different measurements are through Lagrangian Eulerian paradigms. And so those are our only 3 bullets under takeaways. So with that, I will enthusiastically pass the floor off to Mallory.
All right, I'm Mallory Bingham, and so I think most of these breakout groups came up with pretty much the same list of concerns and impediments to MRV and CDR. So the first big one is, what are our standards? And so I think every group kind of spent some time comparing between the terrestrial and the ocean spaces, but putting those boundaries around baselines. What is the standardization of what is a baseline that we trust? What kinds of uncertainties are acceptable, and how are we comparing between different methods? Where do we draw this box around MRV? So it would be a problem if some groups include shipping and logistics and all of these things around a particular method and other groups do not. So standardizing those sorts of boxes are going to be important. Data transparency was a really big topic for all of these groups. These data sharing and data aggregates are something that is a known problem for academics, where there's publish or perish, but when you add in all the private companies that are also trying to commercialize on top of that, we end up in some issues. As Jacob talked about, and as the previous groups talked about, differences between ocean and land, what's shared, what's owned, understanding those restrictions that we're working around are something that's going to be pretty important when there are different groups of different jurisdictions. And for individual PIs, individual scientists trying to build around this, understanding that framework is going to be something that could be a big hindrance to individual groups that are trying to spin up field projects. Similarly, working in the international space gets complicated. Social justice came up in many of these breakout groups. And the idea here is that we can get in on the ground floor, or we can try and fix these sorts of social justice issues later. So is the US taking the lead, or other countries taking the lead? So optics and all of those sorts of PR problems are going to be linked into this, and creating some sort of a standard for what is the minimum that we can approach here is something that people were interested in. And again, the pace of academia and the pace of private industry are always going to be important. So with that, I'll pass off to key questions.
Hi, I'm Ajit Subramaniam, and again, you can see the bullets here. Excuse me, that's not COVID. And I'm going to say that after every class, which there's going to be. So the key questions was basically discussed around the research code of conduct, the need for defining them and getting in early on defining these code of conduct and who's going to do that. We need to make sure that the partnerships that come into play have transparency. So again, it's clear who's engaged. The repeat of the data sharing and aggregation. Here the discussion was really around the idea that we need to know as we take these individual actions, the MRVs have to have a place they can report the data so that over time, our global budgets in some fashion are better constrained. And so we need to talk about how we're going to share this data in the beginning, as opposed to trying to come up with a system later, because this is going to be a key part of our understanding of success of how we're doing this. We need to have a better handle on the co-benefits. And so this is basically an opportunity in any of the CDRs and MRVs, being able to assess co-benefits is going to be a key part of that. And again, you can see that social justice was an opportunity that and important issue that we need to discuss. And Gisela.
Yeah, hi, good morning. Gisela Winkler from Lamont. So I'm going to present the action bullet point to you. We interpreted actually slightly different than the first working group. We thought of it more as sort of actions for our group here. And so we came up with a bunch of ideas for this. We've already heard about code of conduct, but the idea is that this group, or OCB, but then we defined it as more this workshop, and this group should suggest definitions and really define the terms of what we are talking about here for MRV, and also sort of give recommendations as our group that are then guidelines essentially for that, you know, by the appropriate authorities to make these decisions and recommendations. And then in terms of sort of immediate actions that this group could take as part of the outcomes on Friday, one of the things that we discussed is an open letter with community signatures of the participants here, or maybe also of a wider group that demonstrates consensus and is more of an external facing document rather than sort of an internal to the community. That's an idea that Leonard Bach brought up. And the other sort of direct outcome that we talked about is a primer, a 2-pager or 4-pager that would essentially serve as also an outward facing document, and that is sort of a more appropriate venue than the executive summary in the National Science Academy of Science report. And the final point that's here, triaging methods, is something that came up at least in one of the groups where we talked about sort of identifying the weakest link in the different CDR methods that have been suggested, which is also something that could be discussed as part of a white paper. That's it. Thank you.
No highlights.
One thing that we kind of probably that we guys know about
James.
yeah, there's we're thinking about sending actions on
Oh, yeah.
Mics are coming online, folks.
Power of like 3 or 4 page document of flood protection, and NOAA put up this on a carbon dioxide removal. We know that it has only some of the kinds of carbon dioxide removal that we're talking about, but fully others could be good.
Oh, there we go. So I just wanted to ask, who would the intended audience be for a 2-pager like that? Is it decision makers, public, stakeholders, all the above?
This is something that was brought up in our discussion, and the fact is that it would seem that we don't have anything to give to the Congress, for example. Sorry. That's what I didn't want to do into the mic. Sorry, it's going to happen every time I start speaking. The audience would be amongst other people, the Congress, but decision makers for whom a 2-pager with lots of pictures would an easily digestible document on both mCDR and MRV. Maybe 2 different documents, one for mCDR, one for MRV, but that's whom it is.
So I know I talked to someone about this yesterday, but I might suggest that if something like that is produced, that you also try to do a congressional briefing, because I think that would be really helpful. A congressional briefing, like a formal congressional briefing on the outcome of the workshop.
I don't know if Anu is here and she wants to say anything about that. Okay, that is something that she had suggested. This is a very personal opinion, but I feel that this particular group is, although the workshop is sponsored by OCB and endorsed by OCB, this group is larger than OCB, and so some of those recommendations I think need to be made by the larger community.
And this is Jamie. I'll just say that as we heard yesterday, AGU is putting forward a code of conduct around climate manipulations. I think they called it, or something like that. Probably getting that wrong. Climate interventions. Thanks, David.
Ken Bissler here. For the group that has this community letter idea, those can be very effective, but were you talking about a letter about CDR in general, about MRV, or what is the purpose, focus? Can we leave here with this?
I thought you provide the answer, but I know this. It's just the action thing. Just telling this to the group that there was I don't know if someone was there. It was an ocean deoxygenation conference in Kiel, like I don't know, a couple of years ago, and one I think very successful outcome there was that they had this what they called the Kiel Declaration. So they had this big document where everyone basically signed saying, hey, okay, basically only said, well, this is a problem. So I thought that was really helpful in the communication afterwards, because they could just like pull out this letter, say, so I'm not saying this alone. There's like a big community of saying that. So something like a document that enforces a bit more action and gains through that gives us helps us gain traction. So that was a bit of the idea there.
Any last comments before we move into the session 3A? That keeps us right on time anyway. Oh, Heather has one from the chat.
Lydia Kapsenberg. Aspen Institute's working on developing a code of conduct for Ocean CDR. I believe this will be integrated in the broader AGU code of conduct and ethics on climate interventions.
Clarifying note, I guess. Okay.
Okay, so with that, we will move on to session 3A. My name is Patrick Rafter from UC Irvine. Just a reminder to everyone, whenever a microphone is in front of you, to state your name and affiliation is nice too. We forgot to do that a few times yesterday. I forgot to do that a few times yesterday. And I claim all of the anonymous questions that were good. So Okay, so today is models, methods, and measurements, part 1 on permanence. Our speakers, so we have 2 keynote speakers, Matt Long from NCAR and Adrienne Sutton from NOAA PMEL. And then we have a panel with Zeke Hausfather from Stripe, Veronica Tamsitt from USF, Cara Manning from University of Connecticut, and myself. So without further ado, let's get going with our first keynote, Matt Long.
Okay, thanks, Patrick, and happy to be here today and talk to you about my perspective on this issue. Let's see. Okay, so I'm just going to start actually with my sort of key takeaway points. So, if you tune out for the rest of the talk, this is basically, I think, the summary of what you need to know. But my perspective is right now that our ability to do MRV for Ocean CDR is urgent, in part because it's a thing that's inhibiting the growth of the industry. Just doing back the envelope calculations right now is a rate limiting step for technological development. Secondarily, we risk market lock-in mechanisms. So this is the beta versus VHS phenomenology that I think has plagued legacy carbon markets. But if we don't get the technology instantiated into people's minds and practices early, then the market's going to move away from us. The level of investment right now is sort of shockingly scary in that regard. I've come to the conclusion that direct measurement will be insufficient. It will not provide a sound basis for MRV. Because the signal to noise ratios are unfavorable, and fundamentally the signals propagate to spatiotemporal scales that are not accessible to direct observation. So models are going to be critical. And we have models in hand, but they are highly imperfect. But I don't think that's an excuse for not putting them together to support MRV right now with the tools that we have at hand. And so my undergraduate engineering professor used to tell me that if you're going to critique a design, you have to propose an alternative. And so right now we have a framework. We have the elements of a framework for MRV based on numerical models and data assimilation, and we need to start applying it despite its gross deficiencies. As a component of that, I think it's important to recognize that that framework must not just deliver estimates of median effect, but explicit estimates of uncertainty. Okay, so just to convince you that I am not completely delusional and that I have some, deep skepticism for our capacity to represent these systems, I just want to highlight this plot that was shown earlier in the workshop yesterday to point out that, there are large, petagram scale discrepancies in our capacity to represent the ocean sink for carbon dioxide, both in observational reconstructions, which is the upper envelope of cyan lines, and in global biogeochemical models, which is that lower envelope, okay? That situation is not unique to the ocean. Here is a compilation of multiple estimates of the Northern Hemisphere extratropical land sink for CO2 collected from inverse modeling studies. So these are inversion models that represent atmospheric transport and estimate fluxes based on formal statistical methods, using representations of the flow as a linear operator and optimizing estimates of the fluxes. You'll note that the advent of satellite observing technology for atmospheric carbon dioxide has made the problem worse. It has expanded the error bars, and I won't get into the details there. But for illustration purposes, I've noted what the 2030 commitment for nationally determined contributions under the Paris Accord is. And basically, the implication of this plot is that from a geophysical perspective, we will not be able to tell you over the next 10 years whether the Paris Accord has had an impact on the trajectory of atmospheric CO2. Okay, so back to this engineering framework. This diagram will appear throughout the talk, and what I'm going to do is try to walk through the elements of this putative framework in a way that's somewhat agnostic to disciplinary background, but I'd like to highlight a few key conceptual features of each of these components. So I'm going to start at the bottom with ocean physical and biogeochemical models. And I just want to highlight my background here, my perspective coming from NCAR, the National Center for Atmospheric Research, where we work on the development of an Earth system model. An Earth system model is essentially a climate model with a bunch of processes implemented that are designed to enable prognostic representations of the global carbon cycle. So the point is that we can force the model with emissions-driven scenarios and then solve for the trajectory of atmospheric CO2 as an output of the model. Specifically to the ocean, Earth system models contain representations of the biological pump, lower trophic levels of marine ecosystems, and carbonate chemistry. They are also built on top of general circulation models. And so in the context of the discussions that we have here, I think it's worth thinking about sort of categorizing our knowledge systems and understand how they comport with reality. So we have exact descriptions, exact mathematical descriptions of geophysical fluid dynamics in the Navier-Stokes equations. Unfortunately, those equations can't be solved analytically, so they must be solved in a discrete form on grids. And that's what general circulation models do. They implement those numerical solutions. Here's an image of a very large calculation. It was actually conducted in China. And to get the data back, the highest bit rate data transfer protocol was packing a suitcase full of hard disks and flying the data home. This is a 1/10 of a degree ocean model simulation coupled to a 1/4 of a degree atmosphere. And what we see here are the multifaceted scales of ocean circulation. So this is replete with mesoscale eddies, large scale gyre circulations, and many features of the circulation. So a key feature of the dynamics permitted by the Navier-Stokes equations, they are deterministic. So these models are deterministic, but they permit perpetual novelty. And so I'm illustrating that with the Lorenz attractor here, which is 3 coupled PDEs that inhabits this region in state space, never exactly looping back onto inhabit the same point again. One additional property of these chaotic dynamics is that the systems display infinite sensitivity to initial conditions. So if we initialize a forecast ensemble, at some point that forecast ensemble will sort of regress to the mean, and it would be indistinguishable from a climatology. Furthermore, the equations of motion permit scale interactions, and that leads to, they're characterized by this sort of fractal dynamic, self-similarity, and an energy cascade. And that energy cascade means that processes that are operating below those that are explicitly resolved in the model have to be somehow accounted for through parameterizations. And so the implication here, both from a computational cost perspective and from a solution fidelity perspective, is that we need a panoply of resolutions fit for purpose to target particular aspects of the MRV problem. Here's an animation that was provided to me by my colleague Scott Bachman at NCAR. And what this shows is a sub-mesoscale. So this is like a 1/64th degree resolution model. And what you see is that the model is initialized with a large scale. The field we're looking at is relative vorticity. The model is initialized with a large scale field that contains mesoscale variability, but rapidly all those mesoscale fronts go unstable and it manifests in sub-mesoscale variability. These motions are highly energetic and mediate vertical exchange in the upper ocean, right? And so the computational requirements to do this kind of calculation are extensive and generally preclude doing it on scales beyond the regional scale. Okay, so I've talked a little bit about the physical frameworks. I just want to highlight some of the processes that are encoded in models to represent biogeochemical processes. And a key point here is that biology sets, is a key term in the upper ocean dissolved inorganic carbon budget. Furthermore, I've illustrated an equation for computing gas flux, and note that that equation depends on a highly uncertain gas transfer velocity, Kw. that determines the kinetics of gas exchange and very substantially contingent upon wind speed and may involve and may be mediated by surfactants and other characteristics of the surface ocean. I think we're going to hear more about that from David Ho tomorrow. That biological term in the upper ocean DIC budget is a product of ecosystem function for which we have no generally accepted governing equations, right? So in contrast to the physical framework where we do have an underlying mathematical description, we just kind of make things up, okay? We conceive of entities then and we assign them names and we fantasize about how they correspond to real entities in nature. But in reality, our models are not true discretizations. We're not carving nature at its joints, as Bertrand Russell said, but rather we are developing a conceptual representation and then parameterizing it according to empirical relationships in the context of these transfer functions. We do, however, have a very robust ability to represent carbonate system chemistry, and that gives us a capacity to do something like if we have alkalinity in a model, and we can quite accurately compute its effects. Okay, so put these two things together, the physics and the biogeochemistry, we yields emergent dynamics in these models, and I'm illustrating that just with a side-by-side comparison of a simulated air-sea flux field and an observationally based estimate of air-sea flux. And so the global Earth system models, even integrated at this relatively coarse resolution, nominally 100 kilometers, are capable of representing large-scale distributions of air-sea flux that largely correspond to observations. We see, northward flowing or poleward flowing currents taking up CO2. We see equatorial outgassing as a manifestation of upwelling along the equator, and other features associated with these fields. And so the key point here is that there's no sort of air-sea flux. This field is a result of multiple processes interacting, and it's an emergent feature of the model solutions. Okay, so that was a whirlwind tour of kind of the chassis of ocean biogeochemical models. Now I'd like to talk a little bit about data assimilation, because I think this is going to be a key point in ensuring these models correspond to a maximal extent with reality. So data assimilation is a collection of formal tools that are used for a variety of purposes. One of them is to ensure model states that are maximally consistent with available observations. So I'm illustrating that here on the figure on the right, which shows observations of ozone collected from satellite and a forecast model, and then the fusion of the two through data assimilation. Another key feature of data assimilation techniques is that you can get explicit uncertainty estimates, which are a product both of your model and observations. And there's two basic approaches: sequential DA and variational methods. So here's just a little a flavor of how a sequential DA works. You can integrate this might be invoked in an ensemble Kalman filter framework, for example. So you run a simulation, an ensemble simulation, and then have observations at some point in time. You sample the model like those observations, and then add increments to correct the model state, and then continue the integration, okay, to the next observation. So this kind of sequential data assimilation has challenges and shortcomings associated with it. These increments are non-conservative, so they break key components of the model physics. And then there's sort of an art to this process. Inflation and localization, thinking about how information from observations propagates across the model solutions. Okay, another approach to data assimilation is sort of variational techniques or smoothers, and this is exemplified to great success with the ECHO state estimate. ECHO basically integrates a model forward in time or over an analysis period, illustrated by the plot on the right here, and seeks to find, through an optimization of various control parameters, the sort of least squares fit to available observations. So this is this is a very powerful technique in the sense that at the end of the day, what you end up with is a forward integration of the numerical model after you've done this fitting, and you can actually rerun that forward model with the data assimilative state over and over again to generate new experiments. That's useful because it conserves heat, and it propagates information both forward and backward in time. There are a variety of shortcomings to this. One in particular is that to develop the technique, you need an adjoint, which is a non-trivial thing to get, and you just can't do that for every numerical model out there. Okay, so putting these two things together, our capacity to represent the system with ocean physical and biogeochemical models, and our capacity to constrain these models with data assimilation yields a powerful framework that can directly interface with observations in the context of MRV frameworks. And I'm just going to illustrate this here. This is an example from my colleague Moha Garemti at NCAR, and it's actually taken from a study focused on groundwater and contaminant transport. And so the thought experiment here is we have this very simple 2D domain, and there is a contaminant plume evolving in this space, right? And so this kind of represents what we might think of in the ocean as the dispersion of an iron fertilized patch or an alkalinity enhanced patch. Well, a key thing about data assimilation is that by virtue of computing properties of the error covariance matrix, you can actually solve for the places where information is most useful. And in this particular study, that's what Moha has done. Basically, what we're visualizing here is the objective function for information content as it evolves over time. And so there's sort of two dots on this plot. The distinction between them are not particularly important here, but basically those are the areas where observations will be most informative in constraining these solutions, right? So this is a powerful technique or a powerful framework that can guide the collection of observations in the context of real-time deployments. I'm inspired by the work of Pierre Lemarceau at MIT, where he couples that framework, which is the quantitative assessment of the value of particular observations, with the operational constraints of ocean observing assets to yield a sort of a comprehensive framework that says, okay, well, we can fly this glider at a particular speed for, this maximum battery power capacity. And therefore that defines something like a reachability front. That's illustrated in this red line here. And then we can couple that reachability front with this sort of objective mapping of the value of information to constrain our model solutions to yield a decision support framework that tells us where to go collect observations given the operational constraints of the systems we have. Okay, so that was just a very small taste of how data assimilation and models might come together to yield sort of a framework such as both to support observations in the context of MRV and promote synthetic forecasts. Finally, a key thing we need is to invoke the actual perturbations associated with CDR in these numerical frameworks. So here's some challenges, right? We're going to struggle continuously against unfavorable signal to noise ratios, right? So, the analytical precision of an ocean alkalinity measurement is only so good. It's in fact, in many cases, going to be commensurate with the magnitude of the perturbations we expect. We do not have the requirement just of establishing truth in the real world, but rather truth in reference to a baseline counterfactual scenario. And so our ability to do both those things is a requirement to compute additionality. I've mentioned previously, CO2 equilibration timescales are order months. Therefore, any sort of perturbation we might imagine manifests over large spatiotemporal scales, or we might need to know something about the large scale overturning circulation of the ocean. And then, as I've mentioned before, our models are highly imperfect, right? And so we're trying to represent systems that are complex and dynamic with these imperfect representations of those systems. I think that's a particular challenge in the context of unknown unknowns. That's the thing that we need to worry probably the most about, because if there's something that we just fundamentally don't understand or completely unaware of in the system, there's a potential to go really, really far off track. So just to provide sort of a flavor of how this might work in the context of an ocean alkalinity enhancement experiment, we imagine that we have alkalinity added to the ocean. That's illustrated in the red arrow, and we're interested in predicting the air sea flux. I've sort of illustrated that in order to do so, we need to compute some carbonate chemistry, solve for the surface ocean PCO2, and compute that flux. And then perhaps we need to follow this parcel of water along some Lagrangian trajectory that, as it's transported and dispersed in the surface ocean. Maybe we also need to worry about the materials we're using and sort of local scale effects to avoid runaway precipitation or to yield disruptions to the surface ocean ecosystem that might either mitigate the total alkalinity effect or cause otherwise disruptive impacts. Here's just sort of a proof of concept kind of illustration computed with a global eddy resolving model that we run at NCAR. This just shows an alkalinity release experiment, a finite duration alkalinity release experiment at that red dot, and the fields that sort of manifest from that. In addition to sort of GCMs, there is the capacity to advect particles, and here's some results from Veronica Tamsitt, who's in the room here, showing the role of particle advection in tracking dispersion. And I'm going to skip forward here to a couple things. Another key component of this capacity to represent ocean CDR is to think about strategies other than sort of alkalinity enhancement or direct DIC removal. Here's an illustration from an analysis that I contributed to showing projections of the growth potential for macroalgae globally. The key thing that I'd like to highlight here is that the top plots illustrate growth potential. The bottom two plots illustrate a metric of uncertainty that was arrived at by doing a Monte Carlo simulation, exploring uncertainty in the full suite of parameters that contribute to that total effect, right? And you can see that these uncertainty numbers are order 1 relative to the total field in many places in the ocean. I think another thing that I'd like to highlight is that we should not be thinking of a modeling system to rule or that will answer all questions, but rather an interoperable set of multi-scale tools. And this is just results we've seen earlier from Dave Siegel's paper, showing the reemergence timescale of DIC, injected at depth in the ocean. And so we can't necessarily do regional scale surface alkalinity patch dispersion modeling in the same framework that we can do large scale global overturning circulation. So we really need to embrace a comprehensive set of tools. So how might this work? Well, let's imagine we have an ocean state estimation that's leveraging sort of the large scale public investment in observing technology. And we're going to do CDR perturbations in the context of that experiment such that we can compute this additionality term. A key thing here is to represent uncertainty. And the plot I just showed you for ocean CDR is reminiscent of this very familiar climate change scenario plot where a multi-model ensemble has been integrated forward under the context of multiple scenarios. I think it's worth noting that there is sort of a dichotomization of uncertainty that we can leverage that exists in the climate literature. And that's illustrated here from this paper by Hawkins and Sutton in 2009. So chaotic uncertainty is this uncertainty. This is the butterfly effect, right? This is the ability for the chaotic dynamics in a system to retain memory of the initial conditions. Over a 100-year timescale, that effect rapidly diminishes as the boundary value problem emerges as the dominant feature of the solution. Scenario uncertainty relates to the contingencies associated with what people are doing. And then epistemic uncertainty is the structural uncertainty associated with our imperfect ability to model the system. So we might sort of add a category for analytical precision at which we can measure the effects of CDR and switch sort of this, switch the scenario uncertainty to something like operational uncertainty that relates to how well we know what we did in the context of a CDR deployment. Okay, so that's basically the outline there. I just want to highlight a few key points. I know I'm running a little over time, but computational constraints are a fundamental rate limiting step. The models that we'd like to integrate sort of inhabit this three-dimensional space of, you know, we need ensembles, we need models that are complex, and we need to be able to integrate those models at high resolution over large regions. So this implies that we need to be smart about how we encode the models. And this is just an example of what we've done at NCAR with our ocean biogeochemistry model, Marble, where we've designed the model in a software framework to be plug and play into multiple GCMs. Another feature of this computational complexity is the data that is generated. And so that, you know, we can't just think about integrating these geophysical models, but we need collaborative development around analytical workflows. And here are several initiatives that I've been involved with that relate to that piece. Okay, finally, I just want to end on a few concluding notes. This plot shows the basically growth in forecast skill over the past several decades in numerical weather prediction. And what is remarkable here is this sort of persistent increase in the long range forecast skill. And the innovations here are really sort of operational, you know, sort of boring operational things like being able to run large ensembles. There's some projection of the investment in the observing system, but improvement in data assimilation techniques to improve initialization and the ability to run ensembles. And so I think this is an inspirational plot that I think we should take to heart in the context. So my proposal for moving forward is to sort of focus on a modeling framework that is divided into two tracks. As I said at the beginning of the talk, we need to start now with a system that we can apply, a prototype operational system, but then we need to have that system capable of being exploded, modularized, and coupled strongly with observational teams that are enabling innovation in that framework. And I'll end there.
Are we? Next up, Adrienne Sutton, virtually.
Adrienne, when you're ready, Adrienne, you can turn on your camera and share your screen.
Yeah, how can you hear me okay?
Yeah.
All right. Just want to get my screen here. Okay, how's that?
Looks good.
All right. Good morning, and sorry not to be there with you in person this week. I am in pre-sunrise Seattle and in a very dark home. So I see light on the horizon, so I'm hoping by the panel discussion, my camera will work. So I apologize about that. I'm not yet an Instagram influencer, so I don't have one of those fancy like circle light things that that would work in my house at this time. So I'm an oceanographer at NOAA's Pacific Marine Environmental Lab and an observationalist, and was asked to talk about permanence in the context of observing. So I'll build upon the conversation started yesterday about making sure we define what we mean when we say permanence in MRV. because we're a mixed crowd, including folks who may not be familiar with the state of ocean observing, I'll provide a bit of background on what our current constraints are, particularly with autonomous observing. And I'll talk a bit about what our existing ocean observing networks are designed and are not designed to do, just so that everyone is on the same page. And I'll reinforce some of the topics that Matt just brought up with regards to how we use the strength of models and observations together. And then end with some recommendations, which are my personal opinions and don't represent any official position from NOAA. So we were asked to disclose any relationships with organizations in the CDR realm, which I don't have, but I do have relationships with companies that have observing technologies that may be applied to CDR monitoring. So I figured that was important to spend a minute on here. So I work with a team at my lab at PMEL who developed and eventually transitioned one system and one sensor that measure air and surface seawater CO2. The MAP CO2 was originally transferred to Battelle Memorial Institute, who sold it a decade later to a company called Sensors and Systems Solutions. The ASV CO2 we transferred to the Jupiter Foundation to support a wave glider project they had, and also to Saildrone, who's now making them in partnership with our lab for quality assurance. My lab has a cooperative research and development agreement with Saildrone that started in 2015 and allowed us to provide expertise to Saildrone as they started adding sensors to the platform. In return, there was a period of time that we received discounted rates for using the uncrewed surface vehicles, but those discounted rates ended a few years ago. Another thing I wanted to disclose, or rather raise awareness about upfront, is that in any cross-sector partnership like the one we're entering here, we need to be mindful of our different cultures and how they may impact this work. Working well together requires that we understand where our different communities are coming from. So in that spirit of awareness, I just want to name a few of the drivers of culture within the ocean observing community that may not be so obvious from the outside. So ocean observing networks are sometimes designed to meet specific objectives, but out of necessity, sometimes they're opportunistic. This doesn't mean the observing community is not thoughtful or planful. It's just that we're up against big challenges. Ocean observing also involves a large number of collaborators from a variety of institutions, and that's not just within large observing networks. It's the case for one buoy deployed, or one glider, or one float. Oceanographers are specialists, so for issues like CDR that are multidisciplinary, you're going to be dealing with lots of individual scientists with lots of different opinions. And then there are way more mandates and research questions than there's funding for, just to help with scale a bit. And I use this a lot in outreach talks. If we spread out all of the US investments in ocean observing across the entire ocean, for every square kilometer of ocean from sea surface to sea floor, the US spends less than 50 cents per year on sustained in situ ocean observations. Now, obviously, the US isn't the only country funding ocean observing, but at least for ocean carbon observing, the US supports over half of those observations. So it's really amazing to me what we know about the ocean considering those investments, which of course, we've combined with investments and expertise and knowledge from research and modeling and satellites. So this isn't a comprehensive list, but I raise these three examples because I think they're important to be aware of as we develop MRV strategies together. So at this point, I think we're all clear on what permanence means. But in order to develop monitoring and verification standards, we still need to define the time scale that's relevant to societal policy decisions. If we consider permanence at the decadal scale of emission reduction scenarios, then we'll need to monitor at that time scale, and the carbon market will need to account for that time scale. We heard an example of that yesterday of a permanence time scale of 40 years for wetland restoration, which I thought was really interesting. But we'll, of course, have unique challenges with tracking permanence at those time scales, given the fact that we want to sequester carbon in a large, connected, fluid environment that has biology and is undergoing climate impacts at the same time. As Ken mentioned yesterday, we also need to consider developing some standards around permanence of ecosystem impact. These are questions for another workshop, but we have to start thinking about whether it's tolerable that an ecosystem is temporarily impacted by a CDR approach. What impact thresholds will society tolerate? And how do we monitor and model that? Here's a definition of mCDR MRV that was shared yesterday, which I like a lot. But let's not forget another role the scientific community has as independent validators beyond the project scale. You know, tracking whether the global community is meeting internationally agreed upon goals for CO2 reduction. That's the question that Galen raised yesterday about the global carbon budget. So some things that come to my mind are what happens when the industry's annual reporting of carbon sequestration doesn't match what we see in the annual global carbon budget. How does the market respond to that? How does policy respond to that? Now, we've had an imbalanced global carbon budget since the beginning, which is either due to our uncertainty in the natural sinks, which we sorely need to reduce, or due to incorrect CO2 emission numbers that individual countries are reporting. So this approach is, bottom-up budgeting, but at some point we need to expect that we'll also have a top-down approach using satellites tracking atmospheric CO2. So this independent validation is something that we need to be preparing for as well. So I'd argue that the scientific community should play an initial role in monitoring and verifying as the CDR approaches are developed. But at the scale of CDR needed, we obviously can't monitor in situ every project once they scale. But we should be developing the standards and best practices for MRV that would then get transferred to another entity. But to do that successfully, we need to be thinking about that eventual transition from the beginning. So we develop standards that can actually be used outside the ocean science community. I can't emphasize enough how important that is. That's part of understanding one another's cultures and different requirements, so we're able to communicate and transfer knowledge effectively. Now, just to throw out more definitions based on the conversation yesterday, I interpret monitoring as the act of measuring over time. And I'm also talking about observing today, which I define as the act of interpreting and understanding collected data. So that's framing I find useful. Figured I'd share it. So I want to talk about individual observing tools first, then scale up to the networks that utilize those tools. So this is a table of commercially available inorganic carbon sensors and systems that was developed in 2015. And in red is what's changed since this was published 7 years ago. Some systems have new models, some technologies were sold to other companies. Still, no autonomous dissolved inorganic carbon or alkalinity sensors. But in good news, there has been an increase in different pH sensors available, with most, if not all of them, being developed during the X Prize competition that focused on pH technology. So there was the X Prize influx of attention and investment for pH, and that's transitioned to industry over this time. I'm sure I'm missing something in this table, but I just wanted to quickly illustrate that there are limits to what we can observe autonomously, and it has been really slow going finding ample support to develop new sensors. in general, we're able to make the highest quality observations on ships. We're able to make climate quality measurements of surface PCO2 on ships, buoys, and uncrewed surface vehicles. But our uncertainty of autonomous measurements increases for sensors able to be deployed at depth. And of course, these different sensors all have different depth ratings and power needs and size. You can find a list of all the available sensors at a directory that's managed by IOCCP. That URL is shown there. Okay, so some alternative approaches used today that can fill in for those gaps in carbon sensor availability. There's always remote water collection devices, right? When DIC or alkalinity needs to be measured at a time and space scale, that can't be done all on a ship. There are DIC and alkalinity sensors in development and partnerships with those developers, helping to test and validate the sensors and providing more people power to the problem would help more rapidly advance those technologies. And then regional algorithms have been developed to estimate the ocean carbonate system using in situ or satellite-based observations. So here's an example where moored profiles of only temperature, salinity, and oxygen off the Washington coast were used to predict carbonate chemistry. And we could do that at a lower uncertainty than using a small carbon sensor that can fit on those profilers. Now, that would not be the best solution for MRV, given CDR projects would modify those predictive algorithms, but they are tools currently used, and I wanted to mention them. Continuing the sensor tour, here's a table of what the Global Ocean Observing System considers essential ocean variables for biogeochemistry, biology, and ecosystems. And here's a list on the left of what different sensors measure that can be deployed on many autonomous surface and subsurface platforms. And here's where the emerging networks of underwater gliders and floats have a lot to offer, because they're able to pair high frequency water column measurements of physics, biogeochemistry, and biological proxies all together. So Simon Freeman showed a figure similar to this one yesterday. This one has time on the y-axis and space on the x-axis, and it shows the time-space scale of different observing platforms. This was developed by folks in the ocean observing community and has much less of a CDR relevant time-space scale gap that Simon's figure had yesterday. And I would even argue that underwater gliders and surface vehicles are able to fill more of this small spatial scale gap shown by these arrows. And I think this figure has less of a gap because it was developed with networks of platforms in mind. We still have to seek out those high risk, high reward kind of challenges that may result in a, acoustic-like technology where an individual sensor could monitor the entirety of the time and space scale of a CDR project. That would be amazing. But we also need to be prepared that we may have to rely on networks of platforms and sensors. Here's another way to look at these time and space scales with ocean and ecosystem processes featured in the time-space domain. And this helps illustrate that somehow MRV needs to tease out signals resulting from CDR approaches from all this background natural variability that impacts carbon and ecosystems in the ocean. That's the signal to noise ratio that Matt was talking about. So I'm going to move quickly through a few examples of existing ocean observing networks and how they may or may not be able to provide information for MRV. The first is the network of deep ocean buoys, of which only a small subset collect carbon measurements. Individual buoys and buoy arrays have an intentionality behind their placement. The tropical buoys, for example, are designed primarily for observing air-sea interactions and forecasting weather-related drivers like ENSO. Given these are observing assets that are already out there, I've heard interest in leveraging them for MRV, but many of these sites are intended to be long-term observatories measuring the climate baseline. So citing CDR projects that are modifying carbon at those locations may not be the best fit. GoShip is a program of ocean basin scale ship surveys that are repeated about once a decade. And they allow for decadal scale inventories of physical, biogeochemical, and biological parameters that are measured by a group of scientists who are physically on that ship. The Surface Ocean PCO2 network is a mix of platforms shown here at the bottom of this triangle: ships, buoys, uncrewed surface vehicles. It's primarily opportunistic. So, for example, by installing CO2 equipment on ships of opportunity. Much of the design of this has focused on how to synthesize this opportunistic observing data and interpolate gaps so the network can deliver maps of surface ocean PCO2. Both this network and GoShip that I showed on the last slide will likely be tools for that independent validation of permanence when CDR is implemented at a large scale. Someone yesterday mentioned problems with ocean carbon data access. So I just want to make sure everyone is aware that all the observing networks I've shown so far, as well as the emerging networks like BGC Argo, all have publicly available data. In the case of this network, there's an annual publicly available product that supports this data to policy pipeline I'm showing in that blue square. The observations in that data product are paired with machine learning approaches and satellite products to get a global view of PCO2 despite the observing gaps. And that's used to estimate the global ocean CO2 sink used in annual carbon budgeting that I mentioned earlier. All fully documented, all public and transparent. This is not a new approach. We've been doing this now for many years. And the final example I want to share is the U.S. Integrated Ocean Observing System, a deliverable from this system that's led at the regional level in U.S. coastal waters is to provide real-time data to coastal stakeholders. So there could be an important role for IUCE in the delivery of MRV information that those coastal stakeholders are interested in. So let's build upon these existing connections with stakeholders. I agree that models need to be deployed now to help us understand the uncertainty of sequestration permanence and potential downstream risks. That also helps identify what CDR approaches are viable and where and when they're best implemented. This figure shows some relationships between observing biogeochemical models and ecosystem health management, but in the context of CDR, I think it needs these additions. So models can help inform observing and monitoring design by characterizing the time and space scales that need to be measured and the level of the signal in the carbonate system that we should expect. So we need to use them for that. A couple of people mentioned yesterday a modeling study that simulated alkalinity enhancement in the Bering Sea, and it looks like Matt showed something similar. And one of the findings was that the resulting signal in the carbonate system would not be detectable above the natural variability in that region, right? Which Matt also mentioned. And that kind of information from models is essential at this point to inform how and where the CDR approach is applied and how we design the monitoring. I can also see a scenario, right, that Matt described in which real-time data would allow for data assimilating model predictions, particularly as a CDR project progresses through time at those long time scales. And in order to do that on the observing side, we need to better develop and implement real-time quality control of biogeochemical data streams. There's some of that, but we definitely need more work in that area. So to wrap up, we need to define the target timescale of permanence. Given our observing challenges, we need a rapid implementation of models that can start to give us some insights into durability of CDR sequestration, the associated risks or benefits, and MRV strategies. We also need to define roles. I think this community needs to start outlining best practices for MRV. We may not have detailed standards yet, but we need some kind of guidance given how fast the industry will move. That was one thing that was mentioned during the breakout report out this morning, and I totally agree. The industry will move fast. The ocean science community, I think, needs to serve as primarily as independent validator. And in order to do that well, we need to improve our understanding of the ocean baseline. I agree that we need to move from the lab into some highly monitored field evaluations in order for us to test MRV approaches. We also need rapid advancement in sensors for that. And we need to continue research that helps us better characterize durability of sequestration and ecosystem impact. And particularly for the transfer of MRV approaches, we have to stay aware of the different cultures and different requirements that our communities are under to do any of this work effectively and efficiently. And that's it from me for now. Thanks for your attention.
Okay, thanks. So we have a couple minutes for questions for Adrienne, and then we'll move to the panel.
Looks like Heather has her hand up.
This comes from Amal Batarai. What is the lowest depth for consistent measurements, i.e. at what depth do we lose the ability to make conclusions about the material constituents of seawater?
Could you repeat that? I'm not sure I understand the question.
Sure. So this is, what is the lowest depth for consistent measurements? So at what depth do we lose the ability to make conclusions about the material constituents of seawater?
The lowest depth. I'm assuming that question about how deep do we measure in the ocean?
It's not clear, but maybe you could address that and then move on.
Yeah, so I guess it varies for what you're measuring, right? But the decadal repeat hydrography program that I mentioned basically sample at the deepest point where we believe that that the carbon system is pretty stable. BGC Argo measures carbonate chemistry down to 2,000 meters, I believe. Many autonomous sensors have depth restrictions that vary, you know, from 50 meters to 2,000 meters. So there's a variety, but yeah, when it comes to CDR approaches, which would aim to get carbon down, you know, deep near the seafloor, we do have a lot of observing restrictions with regards to how deep we go there.
Okay, so we're going to hold the rest of the questions for the panel. Let's thank Adrienne again, and let's bring up our panelists. Okay, so Veronica, Tamsitt, Cara Manning, Matt. So Adrienne, hold on virtually for the panel.
Yeah, Adrienne and Zeke, you can turn your cameras on if you like.
Yep, they should be on now.
Great. Okay, so I guess Zeke, you are going first.
Perfect. Should I just jump in?
Yep, we're ready.
Okay. So hi, everyone. Thanks for having me here. I'll keep this quick so we can have a good discussion. But for folks who might not know, I'm with Stripe and Frontier is deploying about $1 billion over the next 8 years to catalyze permanent CDR. The idea is we're using this decade to figure out what works and what can scale with an aim of maximizing shots on goal rather than tons removed at the lowest costs. So, we can be in the best position to, pursue solutions at a much larger scale in decades to come. But we tend to have a much higher threshold for permanence than most others in the market. And permanence thresholds are by their nature somewhat arbitrary. We've decided on 1,000 years permanence is required for our purchases, in part because it corresponds with the majority of the residence time of a pulse of CO2, i.e. there's about 20 to 30% left after 1,000 years. Though it's worth noting that the recent IPCC Working Group 3 report refers to permanent CDR as 10,000 years or higher. But permanence is an important criteria for carbon markets. There's standards like the Science-Based Targets Initiative that are increasingly requiring companies to neutralize residual emissions with permanent removals at the point of net zero. There's also a growing push in the literature, as we saw with the recent Allen et al. Review paper, to sort of require like-for-like removals in a net zero framework. In other words, geologic storage should be used for fossil fuels removed from the geosphere. Biologic storage or biosphere storage of CO2 should be used to counterbalance emissions for the biosphere, et cetera. But I also wanted to mention some work that we've done that Freya mentioned as well yesterday to try to better quantify the uncertainties, both across elements of the CDR pathways and also the permanence in different CDR pathways. And it's worth noting specifically that different CDR pathways have very different degrees of uncertainty, both in permanence and delivered tons. And when we think about which pathways to pursue, we need to balance uncertainty, cost, and scalability. It may well be that pathways that are the lowest cost per ton removed are not necessarily the most certain, even when we've tried to internalize that uncertainty into the price of removals. This fact is particularly true for CDR and open systems like ocean alkalinity enhancement and macroalgae sinking, where, as other speakers have discussed, long-term monitoring is more challenging. And one thing that really came out of this work we did with Carbon Plan was that, while individual companies can do a lot to improve the rigor of their MRV approaches, there really is a critical need for systems level work, better modeling, better tracer studies, better instrumentation to provide the level of certainty we need to scale some of these ocean CDR approaches. And so it's exciting to hear a lot of the work that's being done in those areas at this conference. If you go on to the next slide. There we go. So as I mentioned, we worked with Carbon Plan to develop an interactive tool to map different uncertainty elements associated with 6 different CDR pathways, as well as 4 different approaches within pathways. This includes direct air capture, bikers or biomass with carbon removal, enhanced weathering, terrestrial biomass sinking, ocean alkalinity enhancement, both mineral and electrochemical approaches, and finally ocean biomass sinking, both with and without directed harvest. And the figure here shows an example of the CDR verification framework tool. And you can see in the case of ocean alkalinity enhancement through electrochemical means, we're looking at uncertainties in base disposal into the ocean, uncertainties in secondary precipitation of carbonates, the biotic calcification response, the air-sea gas exchange, the DAC resonance time, as well as some other slightly more poorly constrained uncertainties like particulate organic carbon response, et cetera. And the idea behind this work is not necessarily to create a protocol for evaluating these CDR approaches, but rather to map out all the uncertainties so that others then can build upon this to develop more detailed protocols for MRV going forward. So yeah, I'll leave it at that since I know we have a fairly short introduction time here, and happy to answer questions.
Thank you. Hi, I'm Veronica Tamsitt. I'm a research scientist at University of South Florida. I'm a physical oceanographer, and my research focuses on the large-scale ocean circulation and how that influences movement of heat and carbon, particularly using particle release experiments in ocean models and also observations of air sea fluxes. I just wanted to kind of, on this permanence topic, highlight three things, and some have come up quite a bit already from Dave Siegel's nice paper. The first one is that at a given depth, the storage, time of reemergence of carbon can vary over an order of magnitude. So geographic location of where you sink organic matter or whatever it is, it really matters a lot. So just the map from Dave Siegel's paper at the top there shows, 1,000 years in the North Pacific, less than 100 years in parts of the Southern Ocean north of the circumpolar current. The second point is that permanence isn't of storage in the deep ocean isn't one number. It's a very broad transit time distribution. So we have to think about when we say 100 years, do we mean for 50% of the carbon to reemerge? Do we, the mean time scales tend to be quite a bit longer than the mode. There's sort of this long tail. And so thinking about as a community what we mean and how much, which of those timescales is relevant is really important. And third thing I want to point out is just models do a really poor job of ocean ventilation, particularly things like the Antarctic bottom water formation are in the Southern Ocean. And so the other thing is that they're really, timescales can be really dependent on the model resolution. So we did some upwelling experiments in the Southern Ocean and found that the upwelling timescale of deep water is halved when you went from a 1 degree model to a 1/10 degree model. So that's just something to be aware of, that we're relying on models here, but we really need some metrics and comparisons to look at their ability to measure these storage timescales. Okay, thanks.
Hi, so I'm Cara Manning. I'm a new assistant professor at the University of Connecticut. I've dressed up like the biological carbon pump today. So this is like carbon sinking to the deep twilight zone. Sorry to anybody who's on the live stream, we kind of appreciate it. I'll send you a photo later, email me. Hi. I'm a gas biogeochemist, and a lot of my measurements focus on using measurements of dissolved gases to study a range of environmental processes. So what I've plotted here is actually oxygen and argon. So it's not carbon dioxide, but I'm using it to demonstrate an example of where we can have carbon uptake into biomass without necessarily having carbon dioxide uptake into the ocean from the atmosphere. So this is a plot of a data set that we collected in Nova Scotia, where we started taking measurements under the ice in the spring and then monitored as the ice was melting. And so initially oxygen was undersaturated, but as we started our observations, because the ice was thinning and melting, we started to see an increase in oxygen, which corresponds to an increase in photosynthetic activity and incorporation of that CO2 in the water into biomass. But because the system was completely ice covered, there was negligible gas exchange. And we know that because we did a dual tracer release experiment. And so we measured that there was negligible flux. So even though we're seeing this biomass incorporation, there's no air sea flux of carbon into the ocean because it's covered in ice. And then as soon as the system switched over to the ice melting, it switched over very quickly to a net heterotrophic state where we're actually seeing decomposition of organic matter back to the water column. And so in this system, did this phytoplankton bloom under the ice actually cause carbon dioxide uptake? We'll never really know because we didn't measure CO2. And that wasn't the goal of the study. The goal of the study was to look at productivity from oxygen. But the point here is really that it's important to make measurements of the parameters you're actually measuring and not use, not just say you're perturbing one process and it immediately corresponds to a drawdown in CO2, because that's not how it works, right? You can perturb alkalinity without actually drawing down carbon dioxide. And then we can go to the next slide. And so the other thing that I wanted to just make a point here while I'm here, since I'm a mainly a measurements person, is what I'm going to call an inconvenient truth, which I'm just going to read it. It's basically that the existing sensor technology really limits our ability to perform MRV at scale. And so, for example, as Adrienne pointed out, there are like no existing sensors that could measure alkalinity, PCO2, or DIC at depth in a mobile fashion. You can put a sensor at depth that measures PCO2, but it has data quality issues for the range of the signals that we're trying to measure. And so basically what this means is that we have a limitation of sensors to be able to monitor the problem as we're doing these perturbations. So I guess I'm saying it's inconvenient because there's a lot of people out here who are proposing to do these experiments and starting them right now. But my question is, what are you monitoring? We don't necessarily have the technology. And I'll also point out that just putting the sensors into the water is not enough. OOI has been deploying commercially available PCO2 and pH sensors for over 10 years. And there's been almost no published peer-reviewed articles using that data because it's so difficult to use, because there's issues with biofouling, many other issues that you really need a domain-specific expert to be able to look at that data. And so I'll just plug that another OCB working group is looking at best practices for OOI data, and we're going to have a report out later this year that walks through how to use these commercially available PCO2 and pH sensors. So if you're subscribed to the OCB mailing list, if you're not already, please do it, and you'll be able to get a copy of that report when it's available for community review. Thanks.
All right, thanks, Cara. I wanted to point out that Cara's Twitter handle is Carabinate, so that's awesome. Hi, I'm Patrick Rafter. You've met me before, but I'm from UC Irvine. And today we're going to talk about carbon isotopes, specifically C13. So it's one of the stable isotopes of carbon. It's the more rare version. And real quick, fossil fuel C13 is distinct. This allows us or provides us this opportunity to highlight the fossil fuel influence on atmospheric CO2 and ocean DIC. So what we're showing here is a plot of a variety of atmospheric CO2, C13. You can see this trend with time going down towards a more negative value. And this is, if you teach an intro to climate change class, this is the plot you show where you say, this is how we know rising atmospheric CO2 is caused by humans, by the burning of fossil fuels, and because of isotopes. They're wonderful. I'm also an isotope geochemist, I should say. But of course, also this impacts the ocean. Here we're showing a paper from 1993, a so-called new window on ocean CO2 uptake. You may have heard of this before, all of this decline in atmospheric C13 and also surface ocean C13 of DIC. You may have heard it called the Seuss effect by Hans Seuss, who was making these measurements in the 50s. Okay, so this has been around for a long time. I'm one of the organizers. I know it's typically not seen as a classy move to put yourself or like talk on your own session you were organizing, but I had not heard anyone talking about isotopes as a potential tool to be used in MRV. And I just wanted to highlight real quickly that here. So in fact, over the past few weeks, after talking with helping organize this and talking with other people in this newly developing community, I worked with my friends Matas Hain and Ryan Green. Ryan is here. Feel free. Some of you have already talked to him. They're both at UC Santa Cruz. And so we put together a simple toy model to kind of play around with this idea of using isotopes and to find what the sensitivity is, what the signal is to noise here. So the x-axis is time since, so our experiment is ocean alkalinity enhancement. The x-axis is the time since the OAE in months. The y-axis is the change in DIC. So we ran a variety of tests here. And the colors here are the change in delta C13. And I should point out that this is the change, this is the additionality. So we're running a conservative test here where we're allowing the atmosphere to continue equilibrating with this 50-meter deep box. And so what we're looking at here is the signal, the additionality or the additional, the gain of CO2 in addition to what normally would happen with this, with our OAE experiment. And so, as you can see, together, Well, so our current analytical limit is something like 0.1 per mils, parts per thousand. Sorry, a conservative limit would be a little bit higher. So, but you can clearly define in DIC versus C13 space where we can get a pretty strong signal. So more alkalinity added, you get a stronger signal. The slope has this kind of rising value here. So that is because over time, the atmosphere in our conservative boundary conditions here, we're allowing the atmosphere to continue equilibrating. And this is not necessarily the case for everywhere in the ocean. We can find places in the ocean where the isotopes have mostly equilibrated with the ocean. And so we would have an even stronger signal with the OAE enhancement. I should also point out there's another isotope of carbon, radiocarbon. It's not as useful as it might have been in the 50s or the 60s when, after atmospheric weapons testing, we had a gigantic difference between the atmosphere and the ocean. I'm not suggesting we should do that again, but if it were to happen, we would have there would be one upside to that. So the question is, can we observe a change in DIC C13 with OAE? Yes, together with the DIC concentrations. With our test, we find provides these, what I would say are testable predictions for CDR. You add this much alkalinity with these assumptions, we'd expect this C13 value. So that's all. And now we're going to go to the Q&A with the panel, and Jamie is going to MC the Q&A.
Leonard also has a mic to run. So thanks, everyone. Should we start with a question from you all? There are some in the Zoom, which we could kick off with if no one has a, right? Oh, Doug, good to see you. I haven't seen you yet.
Yeah, it just relates to the use of data assimilation and models and sorry. Oh, sorry. Yeah, hello everybody. Doug Wallace from Dalhousie University, and the question relates to data assimilation techniques for this addressing this issue of additionality. I'm just wondering that the historical development of those techniques has been for things like weather forecasting, where things like mass conservation, you mentioned, those rules can be broken, and because you're concerned about the state of the environment at any particular time. And but for this problem, of course, mass conservation is central to the whole question. And the other difference, I'm wondering whether it's important or not, is the distribution also for MRV doesn't necessarily matter, in contrast to maybe the evolution of a pollutant plume in groundwater, but rather the total amount after a certain amount of time matters. So are there fundamental differences in the questions that we're approaching for MRV compared to historical applications and development of data assimilation?
Yeah, I think that working. Really close? I don't think it's working. Yeah, I think you raised great points. I think, the conservative issue is something that needs to be confronted. The attractive element, models have persistent biases, and it's just impossible to move forward without a clear assessment of what those biases are and how they might impact the solutions and the quantity of interest. And so, I think this is sort of a new application in this space. It's also possible, though, to use data assimilation in ways that are not changing state directly, but actually working on parameter estimation. And so I think that present iterative techniques. I'm not an expert in this field, but I think I think the key requirement at the end of the day is to provide clear assessments of the fidelity of the solution with respect to available observations, and to generate states, model states that are maximally consistent with those observations, so as to move forward with the objective, which is to quantify, the effect of CDR. And so I think we're going to innovate in that space to the extent that we have the opportunity.
Tyler Rohr, University of Tasmania. We talked about this a bit at our breakout yesterday, but I'm curious what the panel thinks about the optimal resolution of MRV. So do you envision this sort of kind of bespoke modeling plus OBS approach being able to be described or adopted at the project or deployment level, which would be optimal for the market, as you could kind of compensate individual projects more precisely for what they've actually done? Or do you envision it happening at kind of a more integrated level where you can't kind of deconvolve the effect of each individual project, but you make sure they're adhering to some sort of process-based standards and then are able to compensate them in some sort of mean sense?
I'll try to say something. I think it's a good question. And I think it depends. I think Matt touched on this in his talk. It depends which part of MRV. Like I think for permanence, where in these cases where the global circulation matters, there could be one tool that can answer this kind of permanence question for all the projects. We have a good sense of the timescale. But then for the kind of like local level MRV, where we're trying to observe, plumes and all this kind of tracking locally, and it's going to be dependent on the method, it's going to be dependent on the site and all these characteristics. I imagine that has to happen at a project level. So how we integrate those things, I'm not sure.
I would agree with that and just add that I think, during kind of the startup phase, when we're doing initial field evaluations of these approaches, we are going to have a pretty localized and project level strategy. But once they do scale up, I agree, and we may find that we, have modeling tools that can address a lot of the monitoring, but at least at the beginning, when we're still understanding how different CDR approaches impact the local environment, I think we're going to have to be pretty project to project focused.
Yeah, I'd second that and say that the nth ocean alkalinity enhancement project is probably going to build off a lot of the modeling and knowledge we get from the first. And so ideally we'll be in a world where some of the MRV costs on a project basis are declining as we do more system level.
Great. There's a question on the Zoom from Hervé Clostra that I think might touch on multiple people, which is, I think he's kind of generally curious on the use of OCBs or observing system simulation experiments to design field campaigns, feedback into the models, and I think multiple people might want to talk about that. It looks like Patrick is.
Oh, I just wanted you to define OCB.
Oh, observing system simulation experiment where you, okay, that's just the words, but the definition is where you iteratively use a model to figure out where you think you should put your observing system or where you should measure. Matt mentioned it for a groundwater technique, and then assimilate and then measure it. So model it, figure out where you should put it, measure it where you thought you should put it, assimilate the measurements into the model and see how they pulled the model towards a solution, and then fold that into an iterative process that improves both the measurements and the models. Is that okay? So who wants to jump in on that one?
What was the question?
I think it's kind of a general question of how do OCs figure into this modeling and observational framework for MRV?
I think I provided sort of one example of that, which is to kind of optimize the deployment of observing assets in the context of, a field trial or, a specific experiment. I think Adrienne and I have some degree of accord there, but, I think running models can be very illuminating, even in a very qualitative sense, where you just, you gain intuition about the nature of the perturbation and relationships and signal to noise ratios. And so at one extreme, models can be informative because you can do sort of back of the envelope calculations, think about property relationships that are informative to build intuition about how to approach observing a particular signal. You know, and then the other extreme is this idea of actually developing sort of intelligent decision support frameworks where you're actually deploying assets or navigating assets in real time, you know, on the basis of a real-time data assimilation system that's that's incorporating both the operational constraints of the platforms and the informational content of putative available observations. And so, you know, where we end up in that space, I think, you know, I think we'll have examples of across that spectrum.
I'll just add to that, that one nice thing about OSIs is that you don't actually need to have the technology or sensors to you know, pretend to do the observation. So we can do a lot of these now with the models we have, even envisioning, the observing technology that's either still in development or that we have other limitations on. So there's sort of like quite a big space to do this right now.
I'll just say quickly, so I think that there's definitely a lot of important work that should be done on like integrating models and observations and going back and forth. And that, like, for example, the exports program is a great example of that, right? We're using in situ measurements to try to improve algorithms of carbon export. But what I guess I don't want to see happen is for an algorithm in one place to be used to say that that's universally global. So that's why for exports, right, they went to 2 different sites and measured export at 2 different places, because say iron fertilization in the subarctic Northeast Pacific is going to have very different impacts from iron fertilization in the Southern Ocean. So just want to put that out there that, you know, if we figure out how one system in one part of the ocean works, we can't necessarily apply that to another region. So.
Matt, in your talk, you mentioned, you talked a lot about sort of the computational intensity of a lot of these models. And I'm thinking about, and you showed some examples of, a theoretical, alkalinity project in Bermuda and Station P2. What happens when there's a lot of these projects happening? Is there a way to scale your model so you don't have to run a whole global circulation model for every project? How do you handle, how do you scale that up?
So, I mean, the short answer is I don't know, but I think, we have ideas, and I think, one could imagine developing sort of pre-computed fields using tracer techniques that, provide a set of basis functions upon which you can kind of reduce the problem to a matrix multiplication, under presumptions of linearity, right? So you could imagine kind of a basin scale or a region scale map that says, an alkalinity injection at this XY T yields this distribution pattern and this aggregate alkalinity effect. And maybe you have to compute multiple maps to take care of the linearity problem. So that would sort of put the computational burden onto a one-time big calculation that could subsequently be leveraged across projects. Another approach would be to consider particle advection and to think about, generating a high resolution velocity field into which you see particles, and Veronica's far more expert than I in that space. But you could imagine using the particles to sample background biogeochemical state and compute a long trajectory transformations and flux patterns, and then develop techniques to aggregate across the distribution of particles so as to incorporate rectified effects.
Hey there, Adam Sabash from Oceanographic. One other interface in the system is the sediment water interface, and a lot of these, you're talking about seaweed sinking, even alkalinity enhancement spurring secondary precipitation. I'm wondering what the state of that, observing that interface is, and how we should be thinking about incorporating those observations into models. Thanks.
Thank you for the question about my favorite subject. I mean, we have certainly lots of approaches for making those measurements, but they're not widely distributed, and they tend to be, in special laboratories, and so they're not generally part of ocean observing systems. So again, I think that they would have to, when experiments are planned, that particularly if you expect a high carbon flux to the seafloor, that we need to plan for those measurements. There are things like benthic rovers that can make time series chamber measurements. I've been using aquatic eddy covariance to give you time series of oxygen fluxes, which we can relate to carbon. So there are approaches, and it should be part of the planning.
If it's okay for me to jump in with a question of my own, and also I just want to make sure we engage Zeke, who is like very special to have at the meeting, not within our OCB community that shows up, every time. So I'm curious, like, as this OCB community is trying very hard to engage this topic and be transparent in our uncertainties, possibly even more self-aware of our uncertainties than anyone else. And you're, kind of at the top of an organization that will set the standards for what durable or semi-permanent CDR is. Like, what is the best way that our community can create information products or knowledge, do our science? That's what we want to do, our science, but how does that best support the task that you have at hand?
It's a great question. We've talked a lot about working with the broader community, be it, researchers like yourselves, programs at national labs, et cetera, to try to identify what the biggest gaps are and where we can, strategically direct resources to fill them. One thing that really came out of the MRV uncertainty mapping work we did is that so much of this, particularly for open systems, is fundamental scientific questions that we are as a community going to have to answer, that it's not going to necessarily be a single company that by themselves runs all these models, develops all these sensors. And so, as I think David Hose in the audience put it at one point, somewhat jokingly, at some point, better ocean MRV is just better modeling and tracer studies. And so better targeting our resources to make sure that we're answering some of these big open questions, I think is key. And a lot of folks, as we've heard at this conference, are working on those issues. But yeah, talk to buyers like Stripe and Frontier about your work. We also talk to a lot of philanthropic organizations that are really interested in reducing these uncertainties as well. And so, hopefully that there'll be, both resources going toward the companies in the space, but also toward reducing these uncertainties that sort of help everyone. The other thing I'd mention is that, as we're building frameworks for MRV, we want to make sure that we're optimizing for transparency. We want to both acknowledge that in some cases MRV approaches might be a competitive advantage for a company in the space, but also make sure that we're not sort of using that knowledge in a way that doesn't improve the rest of the space. And so having bigger community efforts, collaborations between multiple companies and organizations operating in a particular CDR pathway, I think is going to be sort of better for everyone. And so making sure we're transparent with the research that's done, with protocol developments, with the data that's collected to the extent that we can is important.
Hi, Nicola Wiseman from the University of California, Irvine. This is sort of a question partially directed at Patrick and others as well, which is if we're talking about sort of methods of verification, including things like using carbon isotopes as a way of accounting for specific anthropogenic uptake, where do you see methods like that fitting into MRV in terms of actual deployment? Are we talking in the planning phases using these techniques? Are we talking in once something is deployed, tracking from there, and sort of where do you see that this accounting fitting in terms of the full project scope?
Well, I'm happy to share the mic afterwards, but yeah, I have thoughts, but I think and I think that's a great question. I think that's definitely something for the community to discuss, come up with solutions for. And I mean, C13 and radiocarbon measurements are specialty measurements, I guess you could say. And there are a few labs that can do that, but there are some advances that can be made in that space to make them simpler. Yeah, personally, I think that would be, for me, this would be like the gold standard for MRV. I'm an isotope geochemist. I would say that. I would want to establish baseline values, then go out there. I would love to have a C13 instrument on a glider. There's all these are future thoughts.
It's been a minute since we took one from the Zoom, so I'm going to relay Brendan Carter's question, which is, where are we with respect to biological monitoring within observing networks? Can we monitor biological consequences of mCDR with sensors that are available now?
Some, yeah. I mean, Brendan would know how we're integrating biological measurements into GoShip, right? But that's decadal sampling, right? There are a lot of possibilities for measuring biological proxies on floats and gliders, and some of that has been integrated and in terms of understanding, particles and chlorophyll fluorescence, on floats, but there's a lot of emerging technology in those areas. I think I showed a list that include, genomics. So there has been work to integrate some environmental samplers on gliders. There's imaging technology that can suss out, what particles are in the water column and what kind of organisms and that's been done on a variety of platforms. You can deploy that kind of stuff on the sea floor to kind of see what particles are falling down through the water column. So there's lots of emerging technology there. But so far, very limited subset has been actually integrated into observing networks.
Alicia Karsbeck from Silver Lining. So this is a question for all of you and maybe for the whole community around models and their use in MRV. So, one of the things that's come up here is the extent to which any of the hierarchy of models we could think about, from GCMs to regional models, whether or not they're really fit for purpose at this point, and whether or not the community can articulate what would make them fit for purpose. And some of those may be, again, general science questions, and some of them may be more specific to the MRV problem. What would be really useful, I think, is if the community could come to some consensus about what are some of the core issues and deficiencies within the model hierarchy that could advance this forward. Your comments on that would be great.
Yeah, I guess I maybe touched on this before. But I think you're right. I think that would be really great if we could come up with the priorities. I mean, one thing I think is that there's a lot of these model intercomparisons, but they maybe don't have metrics looked at that are actually specifically useful for MRV or for permanence in particular. So that might be something to think about, like what, the ways in which we're evaluating model skill that's specific to what our needs are. And, how can we include that in these kinds of model comparisons so that then we can, be clear in terms of how to develop and improve those things.
Let me just add a little. I mean, I think this is a thorny question in the sense that, model biases have been persistent for decades, right? And so we're contending with, and uncertainty in fundamental parameters like the gas exchange coefficient or, our ability to represent the biological pump. These things, are just outstanding issues that our community has been wrestling with for decades. And now I think, our lack of ability to close the global carbon budget is deeply concerning in the context of this societal development, the requirement basically to proactively manage the natural system so as to sequester CO2. I guess one of the things that I think may be a clarifying framework is that if we transition from a mode of sort of academic exploration to a mode of decision support and quantitative generation of quantitative forecasts and assessments that basically are engaged in a real-time feedback loop with the stakeholders that demand that information, will develop sort of a cultural transformation in the community that is clarifying, perhaps. And so, how that manifests in clarity on terms of the modeling requirements, I think, in some sense, there's a co-design process. It's like, what do the stakeholders need to know? Well, let's build, modular modeling frameworks and workflows that deliver that specific information and do explicit assessments of uncertainty.
Yes, I think Galen McKinley, Lamont and Columbia, I think my question really flows very nicely from the last one. What's the funding model to do this, right? I mean, right now, all the observations, whether it's sensor development, whether it's going out to sea, whether it's building the model, are all basically research projects, always struggling to fund them, always struggling to find people, struggling to train enough graduate students. What is the funding model that we can use to accomplish this rapid development? How does that feed into all these many, I don't know, millions, billions of dollars going into the whole process? What's the pipeline there?
Yeah, that's a great question. I'd love to hear thoughts from the other panelists, but from my end, there needs to be a role for the folks who are actually trying to invest or buy from also fund, larger ecosystem efforts around this. We are hoping to have some discussions later this year around organizational design for MRV going forward and what makes the most sense for some of these permanent CDR pathways, how to avoid some of the challenges that we've seen in the past in voluntary carbon markets, but also, the extent to which those organizations that are doing sort of verification or registries can also help direct research money towards some of these problems in some of these areas where there are big uncertainties that remain. So yeah, I would love to continue the conversation.
On the federal side, what would really help is, industries interested in this space that, are not seeing the tools available right now to them, communicating that to, federal agency leadership and congressional folks that actually appropriate the dollars there. Because I think some of them are starting to hear that, but that message really needs to get across loud and clear, I think.
Lori Zulkolsky, University of South Carolina. This is kind of riffing off that question because there's been a theme emerging in a lot of our discussions about how the pace of industry is going that much faster than scientists can keep up with. And so I'm curious from Zeke's perspective in particular, how can scientists actually be involved in this? Because it seems like y'all are moving a little faster than we can keep up with. And so how, in your view, can scientists be a bigger part of this?
It's a great question. There is a real risk, particularly for some of these ocean systems, in scaling too quickly, because we don't want to end up, with another no-till agriculture, an example of an approach where we invest heavily and it turns out to have minimal carbon benefits or CDR benefits. One thing that we've been talking a lot about as a framework is, MRV not as a barrier to innovation, but as a precondition for scale. And so making it clear, what specific milestones need to be passed in terms of MRV processes in order to get from these early sort of prototype projects to, big offtake agreements and large scale deployments. And I think that process hopefully will provide a little bit more clarity around the major areas where we need more basic science, we need more modeling and involvement from scientists in the field to sort of close those gaps and to get broader confidence among the community of buyers that some of these ocean CDR pathways are ready for large scale.
Hi, Grace Andrews from Vesta. My question is for Zeke. Something you said, your opinion, Stripe Frontier, and it was brought up yesterday by Carbon Plan, is the role for system level, a system level role in MRV. And just to say, I really agree with that. Sitting from the seat of being in a startup, I mean, the sort of intensive modeling programs that we're talking about that I absolutely agree is necessary to build trust in the carbon market. This is something small scale startups aren't resourced to do. So a system level role, I think, is absolutely essential. At the project sale, shameless plug, if you want to work with us, let me know. Okay. But at the system level, that's the concept there, I think, is on point. But what does that really mean? Who do you think is the best, who's positioned to take on that role from your conversations? And, related to that earlier comment, how do we get the funding to whomever that's going to be ASAP? And I'm asking you, Zeke, because Stripe has obviously played like a tremendous role in accelerating the field of innovation here. And I think that this is going to be a blocker that I'd love to have us really start working on today.
Yeah, I don't have a concrete answer right now, but we are sort of kicking off some processes and some additional conversations with a wide variety of industry, government, and academic stakeholders later this fall to try to start addressing some of those questions. I think that at the end of the day, it's hopefully going to be a combination of money from buyers, money from philanthropic organizations, government resources. The challenge is figuring out the best framework to deploy those resources toward answering some of these system level problems. And again, I don't think we have the answer today, but it's definitely something that's top of mind for us, and we're trying to figure out ourselves and talk to everyone else.
Okay, did you want to make a comment on that question? Go ahead.
Yeah. Hi, I'm on the panel, Patrick Rafter. I'm just confused by these two words, system level. I'm still confused, and everyone's talking about it. I imagine other people in the audience are also confused. Could you just elaborate on what you mean by system level?
So in the context of the type of MRV work we're talking about here, it's sort of what process improvements, developments, modeling should be done by individual CDR providers, individual companies who want to do projects, and what work should be done by national labs, universities, consortiums of academics funded by the government to sort of develop their modeling to support, and allow companies that are deploying CDR to reduce uncertainties. I guess sort of the system level work is what should not be the responsibility of a CDR company to be directly doing themselves. What sort of supporting work needs to be done by the broader academic community?
Okay, I want to end on a couple of, we have 2 minutes left, and I want to raise a couple of really compelling questions that have come in on the chat here that could really, they could go into the breakout sessions, because I think they're kind of overarching questions that we should spend a little bit of time on. One of them involves CDR implementation locations. This comes in from Jinping Hu. It seems no one has talked about CDR implementation locations. While any CDR approach may face the risk of infinite dilution and mixing in the open ocean, Would it be feasible to apply CDR plus MRV scheme in a more well-defined and characterized mini ocean to start with? For example, the Gulf of Mexico, the Mediterranean Sea. This way, the signal may not be diluted too much, which makes both measurements and modeling easier with better accuracy. And the other comment I want to raise comes from Samantha Siedlecki from University of Connecticut. Despite the notable limits and biases that Matt pointed out, models are being used to support decisions already. Projections being used in international policies, regional forecast systems relied on for marine resource and hazard management, marine spatial planning, observational system design. This is a new stakeholder to consider in that existing space. For new stakeholders, it's important to understand the timescale of importance, the current information available to make the decision, and what metrics and variables they planned or actively rely on. I see the conversations here seem to be informing those questions. We can then pair evaluation to be tailored to those questions. In my experience, model evaluation has been limited to place-based comparisons, and it seems here we are asking the models to move to a process-based evaluation space. I think this is a move we've been wanting to do and is an exciting space to consider establishing protocols around a process-based model evaluation together with observing programs. So I think those are two really compelling things that I'd love for you to take into breakouts as we come up on the last 3 seconds of this session. So thank you, everybody.
You're one of those.
I like the. Yeah,
That was okay.
like.
So.
Yeah, I mean, it's a huge transit time distribution. Yeah, so.
Well, you know. All running really, but do it. I've been thinking those. What was
Back at 11:10.
Thank It's okay. Sure. I'm just gonna put a slideshow and you can go through.
Great.
And I'll be having you guys just go swap.
Yeah, right. Totally, that's good. I think this shared thing is great for eliminating the transition time. Exactly. Lots of animations there for Jacob. Wonderful. They all seem to be fading in. Great.
I'm gonna put your slide up. How do you?
Yeah.
Hi, everyone. I'm Manon Berger. I'm a PhD student in Paris, and I'm working on assessing macroalgae CDR using an ocean biogeochemical model. So what we did is what we grew and harvested kelp in economic exclusive zones with appropriate temperature and nutrient ratio. So we ran two simulations, one where kelp production was simulated as a uniform and unconstrained carbon sink. So what we can see in the first animation is the additional monthly carbon uptake. And even though the input was uniform and constant in time, the response air flux is highly variable in time, and also it spatially extends way further the initial cultivation mask. And we ran another simulation where kelp production is nutrient limited, and we are accounting for phytoplankton feedback. And here in the additional monthly carbon uptake, we can see red area, which corresponds to area where kelp cultivation results in a reduction of the carbon uptake, which is not what we want. And then we looked at the local CDR efficiency, which we define as the amount of atmospheric carbon removed from the atmosphere relatively to carbon removed from the ocean. And what we saw is when we did the first simulation where kelp is just simulated as a carbon sink, so this accounts only for physical and geochemical processes. The local CDR efficiency is widely variable in space, and it's mostly below 100%, from 5 to 85%. When we account for nutrient constraints and phytoplankton feedback, it decreases the efficiency, and especially in the tropics and nutrient limited waters. So the take-home message is that half of the RC carbon flux, additional RC carbon flux, is occurring outside the cultivation area, potentially hindering MRV and causing transboundary issues. Then physical and geochemical processes limit the CDR efficiency, and nutrient constraints plus phytoplankton feedback further limit it. So maybe measuring the weight of macroalgae biomass won't be enough. Then in our analysis, out of the 75 million square kilometers where kelp was grown, only 0.3 had exhibited a local CDR efficiency higher than 80%. So we are currently preparing a paper, and it will be submitted soon. So don't hesitate to reach out. Thanks.
Hi, everyone. Yeah, hi, my name is Burt. I am the Chief Ocean Scientist for Planetary Technologies. I'm joined this week by Dr. Greg Rao, who is the Chief Technology Officer for Planetary, sort of the guru behind our process. So I just want to quickly talk about what we do at Planetary and what we are doing in the space of ocean alkalinity enhancement. That is what we do. We sort of do it in 3 steps. We manufacture alkalinity in a low carbon intensity way. That is the technology that we are developing. And we focus most of that on magnesium hydroxide. We deploy that alkalinity through ocean outfalls. That's fairly important because those outfalls have clear permit limits and they use existing infrastructure. And I think for a lot of the MRV, using those outfalls will also make things a fair bit easier. Yeah, and then we verify the captured CO2 in seawater, which of course is very easy, as we're all learning about this week. But we're doing that as well as studying the biological impacts with a lot of academic partners. So I want to acknowledge our team today as quickly as I can. Mike Kellen, the CEO in the top left, really inspiring guy to work for. We have sort of a metallurgy team working on the alkalinity production, sort of almost a business strategy team working on locating these outfalls and understanding and working with outfall operators. And then this is our ocean team, which is actually growing quite quickly now. We just brought Yuan in. She's brilliant. And some more sort of internships have started in this oceans team, just to say that 2023 is going to be a pretty big year for Planetary. And I hope we can bring in lots of other team members into our group. So when I say that we're doing ocean alkalinity enhancement, I really mean it. We really are doing it. And I want to explain sort of what that means. So we're doing a lot of research with various different partners, mostly with Dalhousie University, as we're located in Halifax, or most of our oceans team is located in Halifax. So that involves laboratory experiments, pool scale. We're doing biological impact, mesocosm experiments, and a great deal of modeling with some very brilliant people who are here in this room. We spoke yesterday about pre-permitted test sites. I want to make a plug for the one we have started up in Halifax, or one, if you've heard of the term Bedford Basin, that's that little green box in the top left corner of that model simulation. A really good spot to have a pre-permitted test site. So keep working on that. Natural Resources Canada, we're going to be doing phytoplankton mesocosm experiments at their facility. University of Miami is doing work on coral restoration in terms of co-benefits for ocean alkalinity enhancement. We teamed up with Plymouth Marine Lab just this month to conduct our first real ocean experiment in the UK. I suppose they acted as our IVVs, a thing I just learned about 2 hours ago. And that was a really brilliant team effort. More to come in terms of what we learned in that study. We have built our Planetary has an MRV framework that we built in collaboration, very close collaboration with Shopify, our first and purchaser of carbon credits, pre-purchaser. I'm happy to talk more. I've been speaking a lot yesterday about how that process worked one-on-one between Planetary, Shopify, and the groups they brought in to build that framework. We have a science and technology code of conduct that we'll be publishing, I think later this month or next month, which has been a really big part of what we've done this summer. And that's probably all the time I have. So my takeaways, Planetary is really doing it for OAE. OAE seems to be, is going to work. And I think that we have to build an MRV that balances provable accuracy with cost effectiveness. Easy, again, like I said. But we're growing, and I really hope to leave this week with a whole bunch of new collaborations that we can build as we take off into 2023. Please look us up. Please come chat with us. Thanks.
I'm Jacob Cram. I'm at University of Maryland Center for Environmental Science, and I want to talk today about the biological pump. So this involved a lot of carbon dioxide removal processes. Stuff tends to form on the surface. Some fraction of particles form the surface. What? I'm not really. How do I look at the? some fraction of stuff that sinks out of the surface the forms of the surface will make into the midwater column. So stuff, I mean particles, aggregates of phytoplankton, fecal pellets from zooplankton. Some fraction of that will clear the middle water column and make it into the deep water column. And I'm interested in how much of the stuff of the particles clears the middle of the water column, so the mesopelagic zone. And I've been combining models and observations of those particles and how they behave. So I'm not going to get into the details of the model, but in general, you get most sequestration of particles when they sink fast or shrink slowly. So you can imagine if you have two particles, one sinking fast, the other one sinking slowly. The one that sinks slowly has more time to break down. There's less of the slow sinking particle left when you get to the deep ocean. Similarly, if you have two particles sinking at the same speed, one of them breaks down quickly, the other one breaks down slowly. The one that breaks down quickly, there's less of it left. So a number of factors contribute to these things. So if we have larger particles generally sink faster than smaller particles. When they're heavy, they sink faster. If the water is cold, the particles sinks, the microbes on the particles are more sluggish. The particles break down more slowly. Oxygen, microbes are more sluggish when there's no oxygen. And with these sort of models, we can build maps of essentially how much stuff makes it to the ocean. So here, redder stuff is redder regions, more particles make it deeper. Some other factors are emerging is also really important. Microbial diversity. So which microbes are on particles? Are they suited to breaking down those particles? How many of them are present? Is emerging as a really important factor. And also zooplankton. Zooplankton break big particles into small ones to move from the large to the small particles. Less stuff makes it through the mid-water column, but also zooplankton produce fecal pellets at depth. That essentially gives us a head start on how deep they sink. So just to close out a couple of thoughts about measurement, reporting, and verification. One is where particles sink and how deeply they sink affects how long the ocean stores them. We've talked a little bit about this in the meeting, but I point out that the National Academy's report that a lot of us read for this meeting and CMIP models in general tend to assume that carbon attenuation is the same everywhere, but for that map, it isn't. Some places stuff makes it much deeper than other places. In ocean carbon fertilization experiments, looking at that map that Ken showed us the other day, coincidentally seem to have been done in the places where transfer efficiency is high, where particles sink really deep. I note that iron fertilization, other CDR approaches essentially rent storage. They store carbon for some amount of time. Longer rental you could think of as having more value. And I found integrating optical measurements and models to be a good way to measure or to measure processes that I'm interested in. I think they could be brought to bear on CRV. Thank you.
So I'm Richard Dewey. I'm with Ocean Networks Canada. And Adrienne gave a great overview this morning about some of the large scale ocean observing systems. And I'd like to talk about some of the more regional ocean observing systems that are perhaps not built for this exact application or for monitoring or doing MRV development, but I think can be modified or utilized almost immediately. This is Ocean Networks Canada's observing systems in the southern part of British Columbia. We do have things in the Arctic and on the Atlantic coast as well, but this shows our coastal observing system in the Sailor Sea, and then the Neptune Observatory off the west coast. And just south of here is the OOI installations coming off from Oregon out to the axial seamount. So similar sort of footprint on the just south of this. But this gives you an idea of the range of our installations from coastal environments like Sandwich Inlet, which is a hypoxic inlet, low circulation, again, could be a laboratory for low oxygen environments to see how degradation of sunk biomatter, for example, responds across the continental shelf, down the slope, through canyons, out into the deep ocean. And in each of these sites, we have a spider web of sensors going out perhaps as many as 10 kilometers with a variety of instrument packages, with cameras, various sensors, measurements. And at most of these sites, we have baseline data going back 10 to 15 years. So we already have some baseline understanding of the physics, the chemistry, and the biology in these sites. And all the data from these observatories is available immediately online. And we're fit for purpose for process studies. I think not necessarily an MRV percent in once we go to scale, but to close some of the process studies, to understand exactly what might happen to sunk kelp, for example, across a variety of ecosystems at the bottom we could do some process studies, recover that kelp or bales of kelp, for example, every few years, and do the assessments to understand the processes to which we're going to need to be able to bound the models and so forth. So some of the existing activities, I want to point out that Oceanographic Canada already has a major CDR program called Solid Carbon, and this is a geological storage in ocean basalts. So it's not really talking about the water column. The water's in the way of getting the carbon deep into the ocean basalts, but we do have an active program called Solid Carbon, which is dealing with many of the same problems. Oceanographic Canada is developing our own MRC framework where the observatory could be utilized. Accelerate design and permitting control field trials. So again, what are the processes that we need to bound these problems? Measuring and quantifying scale impact, particular for time series analysis at fixed sites. Again, we're not mobile assets at the moment, but we're fixed and high resolution. Again, we've got established networks covering a range of marine processes and long existing baseline measurements. So we can make, I understand the existing distributions of the variable, the environment onto which we might perturb. We have existing support for almost all sensor types, not all sensor manufacturers, perhaps in the PC world as it's evolving, but we can easily adapt and put new sensors on the observatory. So I just like to make sure for these field studies, which we'd like to get going really rapidly, there are some facilities that can help us bound some of the process studies. Thanks.
I'm Alex Gagnon. I'm faculty at the University of Washington, and I want to briefly share with you a project where we're using the really fine and weatherable particles that are produced when glaciers grind across basalt or granite as a natural analog for alkalinity addition to enhanced weathering. So we're studying these particles as they're introduced by tidewater glaciers into fjords. And you can see here in the upper right, here's an example of some of the sea ice that we collect that calves off of glaciers. You can see the large particles there, and you can see the milky character of the water in these fjords, which is due to the suspended particles that are very fine and very reactive. So we take advantage of the natural estuarine circulation that are characteristic of these fjords and do geochemical measurements across this, this flow path, geochemical measurements of carbonate system parameters, trace metals, number of isotopes that have potential for MRV, including lithium isotopes and C13, as well as measuring sediment fluxes to be able to make measurements of weathering rates and alkalinity addition rates in real world seawater conditions, as well as inferring carbon dioxide uptake and assessing co-benefits and potential risks like heavy metal addition. This is one of the advantages of working at our study site in Prince William Sound is that there's a number of different fjords, and each of these, because of their different geology, means that we have a bunch of different effectively chemical reactors from where we can test this under different geological conditions. These are great study sites for understanding CDR and for developing MRV approaches and protocols. So we've done two field experiments this summer, and we're busily analyzing our samples. This is collaborative work done with my co-investigator, John Crucius of USGS, as well as with collaborators Rob Campbell from Prince William Sound Science Center and graduate student Mary Margaret Stoll, who's in the audience. And we're really grateful for funding from Ocean Visions and Climate Works. This focus, excuse me, on natural analogs, I think is really exciting because it's a way that we can do CDR right away. And the permitting requirements are non-existent or small, and it really embraces this sort of do no harm philosophy, which also resonates with our team. Great. So I'm going to pivot just here briefly because I also, since this summer, wear another hat as the leading a direct carbon dioxide removal from seawater startup company that spun off from the University of Washington. This was Banyu Carbon was co-founded with Julian Sachs, another professor at the University of Washington. And in its simplest sense, what we do is we take seawater and we extract CO2 for sequestration or utilization. And you've probably heard of processes like this that usually rely on electrochemical approaches. Our approach is we're developing a fundamentally different approach because we're able to couple a photochemical process so we can use light directly to drive CO2 out of seawater. And briefly, in the last little bit here, if you zoom in on what's at the heart of our process is a class of small organic molecules that when they're illuminated by visible light, they dramatically and reversibly change their acidity. And so we can use this to drive CO2 out of seawater, or in some modalities to lead to alkalinity enhancement. It's a reversible process. The synthesis of these is simple, requires no rare earths or heavy metals, and they're incredibly efficient at harvesting light with quantum yields up to 70%. So super excited to talk more about these, and both for my academic lab and for Bonding Carbon, we are hiring. And so look out for those ads, and excited to talk with everyone here throughout the week.
Okay, so we're going to go into breakouts, and I want to remind you there's a participant resources folder that has all the breakout assignments. We've moved there were originally 2 breakout sessions happening in here. We're going to move one to the front of the room, and then we're going to move the other one outside. So just look at the printed assignments or look in the folder to figure out which one you're in. Also a reminder that in the participant resources folder is a document where we've been compiling virtual participant questions that have been coming in during the plenary sessions. And that's where I got those 2 compelling questions from Samantha Sidlecki and Jinping Hu for us to be thinking about during these breakout sessions. There are also prompts for your breakout discussions right here in the agenda with regard to permanence, what needs to be measured, what can be modeled, how does that change with the scale of the intervention, and how can we use models to inform what and where to measure. So all really good content. You're going to go into breakouts for about an hour, and then Jessica, what's up?
I was going to say, if you're a session leader and you want access to those Google Drive documents we've been working on, they should be in the participant resources folder now. So you don't have to use them during your breakout, but it's there for you as a resource.
Yeah, and you'll notice I have those big, huge sticky papers all over the breakout rooms with lots of sticky notes. So if you want to engage in any of your own brainstorming follies, please feel free to do so. And also, please remember, the breakout leaders are responsible for meeting in a synthesis group to discuss. So that either will happen for the morning breakouts, that will happen at lunchtime for the latter half of the lunch hour. And for the afternoon sessions, that will happen first thing the next morning. So you need to be sure to take the early buses. So this is all, just look in the participant resources folder. Everything you need is there. And if you have any questions, just ask. Go forth and have fun.
Yeah.